Hi, welcome back. Okay, Chapter 7, Video 1. Alright, so we're going to skip Chapters 2, 3, 4, 5, and 6. And if there's anything from those chapters that you need to know, I'll tell you what they are. And do understand that the things that I've skipped really should be a review of middle school science. So first of all, again, here's a teacher that you can match my voice to. Again, students learn better when they can see a teacher. And look at the joy on her face. She is so happy. There's joy in teaching chemistry, and this I know. All right, so for Chapter 7, I included the... Why would I pick the pen color to be black? Anyway, Chapter 7. For this, I would go and print out a blank periodic table. I included it in the Chapter 1 notes and materials, or you can go online and just type in blank periodic table and print what I did. I stole this right from the internet. I don't even know whose periodic table it is. And because you're going to want to have something that you can write on that's organized like that. And then also print out a regular periodic table, one where you can zoom in and see the mass numbers. And I will pause and give you an opportunity to go and do that. Okay, I paused, and you're back. Great. All right, so what do we got to do in this chapter? Or at least in this video. Let's see what we got. We have on the agenda chemical symbols like H and 2 and O for water. Again, stuff from middle school you probably already know. The mass number based upon the isotope that we're dealing with, the nuclear and electronic charge, how to determine the number of atoms in a formula, and what is the difference between an element and a compound and a mixture. And then I'll save chemical and structural formulas and atom inventories for the next video. Okay, first of all, difference between an atom, an ion, and an isotope. As far as I'm concerned, they all fall under the same category. We are dealing with particles. And these are the particles that we are going to combine into chemical structures. They're not the only ones. And they think that you learned this in middle school. This is actually done in detail in Chapter 3. We'll go over Chapter 3 later in the course when we talk about matter and energy again, and we start to talk about thermodynamics and the first law of thermodynamics. All right, so an element versus a compound. Now, when we speak of elements, elements are groups of atoms. And you know that an atom has a nucleus, it has electrons, and they say that these are fundamental building blocks of chemical structures. Now, fundamental means the smallest structure you're going to deal with. Now, the truth of the matter is the atom is not the fundamental particle in the universe. If you take an atom and you smack it open, you know that protons and neutrons come flying out of it. And if you take the protons and neutrons and smack them open, then you get quarks, and you continue to smack them open until you get down to little strings of energy. So when we're talking about fundamental particles for atoms, we're talking about things that have an identity. For instance, there are different types of atoms. There's gold atoms and silver atoms, and a gold atom is different than a silver atom. However, when you smack open those atoms and you look at the protons and neutrons, you can't tell the difference between a neutron that came from a gold atom and a neutron that came from a silver atom. And so therefore, when we talk about those particles, we don't talk about them in terms of the fundamental building blocks to create chemical structures. All right. So when we talk about element, an element is a group of atoms. An atom is a neutral fundamental or neutral particle. Okay, protons, neutrons, electrons. Great. We remember that from third grade. An ion is when you have an imbalance of electromagnetic charge. In other words, there are more electrons than protons. And when I talk about force, we're going to start to take a look at positive and negative charges and start to think of them as deficiencies and surpluses of charge. And I'll get into that later. And an isotope is when you have different varieties of the same type of element. For instance, hydrogen, there's actually 3 types. Hydrogen with no neutrons, called protium. Hydrogen with 1 neutron, called deuterium. And hydrogen with 2 neutrons, called tritium. And although they all behave similarly, they do have slightly different properties, but they do behave chemically like hydrogen, and we'll talk about those in chapter 4. So again, when they're talking about ions, isotopes, atoms, again, they're just talking about particles. We're going to deal with how we symbolize those particles. Okay, well, let's go back to that first screen. All right, chemical symbols. All right, so if you go to the periodic table, which gives you all the different types of atoms, you know from middle school that every time we have a capital letter, it symbolizes a different type of atoms, and a lot of them you already know. You know C stands for carbon atom. Oopsie poopsie. C stands for a carbon atom, and H stands for a hydrogen atom. If you have a capital letter and a lowercase letter, that represents still one type of atom. For instance, if you have C with a lowercase o, that represents cobalt. And I'm going to clear up something right now for you as I go through these slideshows. Whenever I do a capital I, I'm going to put the little bars on it. And a lowercase I, I'll do with a dot. And L, same thing. I will add a bar for capital L, and I will just do a straight line for lowercase l. So when you do Cl, that's not Ci, that's not carbon iodide. That is just the atom chlorine. Now be careful with some of this. You have to make sure that you distinguish between capital and lowercase, because if you write cobalt and you write capital C, capital O, that's not correct. This is actually a compound called carbon monoxide. And it consists of one carbon atom, one oxygen atom. Actually, we're going to learn that the IUPAC, International Union of Pure and Applied Chemists, called this carbon-2 oxide, Roman numeral 2. We'll get into that in another video. Be careful also. On the test, you're going to have a periodic table. It'll have the symbols and it'll have the names. So one of the things that really irks me, although you won't be doing this on free response, you'll be doing it on multiple choice, but when you get to the AP level, if I ask for fluorine and you write, you lose a little bit of points there. Instead of giving you a full point, I'm only going to give you 8/10. I'm going to take off 20% because that's fluorine. It's not spelled that way, and the spelling is right on the periodic table. So do get used to looking this stuff up on the periodic table. Also, understand that not all of the elements were named via English names. So for instance, if you go to look for copper, it's not going to be CO. It's going to be capital C, lowercase u, from the Latin term cuprus, or cupric, which is Latin for the term copper. Or lead comes from the Latin term plumdum. So make sure that you're looking this stuff up. Okay, so there's the symbols. Oh my God, reviewing middle school is so boring. That is the loudest neighbor. Anyway, moving on. Mass number, nuclear charge, electric charge, number of atoms. Okay, so in middle school, you probably did something called isotope notation. Now, when we write a symbol, there's 4 places for numerical information. Let's say we're dealing with chemical X. There is no chemical X. But we have 4 locations for information. One location in the northeast corner, and that location we might put a number like 2 with a negative after it. And in the southeast corner, you might have a number like 2. And over here, you might have in the northwest corner, number 16. And in the southwest corner, number 8. Okay, what do all these numbers represent? In the northwest corner, this is called the mass number of that particle. And the mass number is equivalent to the, I'm going to put the hashtag, meaning number of protons plus the number of neutrons. Now, in terms of coming up with the mass for the particle, why are they not including the electrons? Well, the electrons, although they have a large volume, they are very lightweight. It takes over 1,800 electrons to have the same mass as a proton, so we exclude the electrons from this calculation. Number 8, down here in the southwest corner, this is called the atomic number. And you probably remember from middle school, the atomic number represents the number of protons, and it gives you the identity of the atom. And with the atomic number, we could now go to the periodic table and we could look up element number 8. And if we find element number 8 on the periodic table, it is oxygen. Right here, element number 8. So not only does that give us the identity on the periodic table, but that number right here represents the number of protons. So now we know that this particular particle is oxygen. Okay. In the northeast corner, this represents the electric charge. And what it represents is the difference between the number of protons and number of electrons. And what I want you to start thinking of is whenever there is a negative, that represents a surplus of negative charge. All atoms have negative charge. They have a positive nucleus. They are surrounded by negative electrons. So this idea of something being positive or negative, I mean, all of them have a positive and negative. So if we say that something has a 2- charge, that means it has a surplus of electrons. And if it has a positive charge, then that means there is a deficiency of electrons. So we're going to consider that a deficiency of, oh, I didn't complete the word negative charge here. Oopsie poopsie. Deficiency of negative charge. And we'll talk about electric charge and electromagnetic force in a few moments. Last place for numerical information around the symbol is here in the southeast corner. And this represents the number of atoms in the sample. We're going to just say substance here. Number of atoms in the substance. So we would have 2 of those atoms. So what would they ask you to do with this isotope notation? First of all, let's not be sloppy here. Let's keep your notes organized. Isotope notation, and that's actually found in chapter 4, but I know you remember it from middle school. Now, don't be like my honors chem kids from this year. They told me they learned nothing in middle school. Not a thing. They just had nice decorations. I don't believe them. I know they learned stuff in middle school. But anyway, so they'd ask you on a test, hey, what are the number of protons in this substance? We know it's 8 because of the atomic number. What are the number of neutrons? Well, the neutrons are the mass number minus the protons. So this is 16 minus 8. There are also 8 neutrons. They may ask you, they meaning me, the number of electrons. Okay, so then we have to take a look at it. If you have a charge of 0, you know the number of protons equals the number of electrons. If you have a negative charge, that means you have a surplus, so you have more electrons. And if you have a positive charge, that means you have a deficiency. You have less electrons than protons. So in this case, we have a surplus of 2 electrons, which means that we have a total of 10. 2 extra electrons. And then they will ask you, hey, what does X represent? And we know that X represents an oxygen atom. How many oxygen atoms in this substance? 2. Okay, let's go back. I'm old. I got to see what I remember. All right, nuclear charge, we talked about atomic number, electric charge, and ions, and then the number of atoms in the substance we talked about. And then we talked about the difference between ion, isotope, and atom, difference between element, compounds, and mixtures from chapter 3. Okay. There are 2 types of matter. So let's organize again our notes here. We'll say the 2 types. First type we call pure substances. And the second type are mixtures. Now, there's not much difference between these. And we'll talk about these in Chapter 3, what the differences are and how to separate them and what their properties are and what makes them different. But the truth of the matter is, all of these substances are governed by what we call Coulomb's law, electromagnetic force. In other words, what are the forces that keep the particles together in your arm? I mean, there are 4 forces in the universe, right? We know that there is gravitational force, warping of time and space, and then we have electromagnetic force. Let's call this forces. And then there's the strong nuclear force and the weak nuclear force. All right. So we have molecules in our arm, and those form tissues and muscles, and in our arm structure with skin. And so what keeps all of those things together? In other words, here I am. I'm awfully thin here. And I'm going to, I don't know, overhand throw a ball. Wow, that's a long arm. All right, so when I throw the ball, if what kept my arm together was gravitational in nature, my arm, here's my fingers, would follow the ball. Eventually it will get to a point where it reaches a maximum where it goes away, and then everything would come snapping back into my arm. That is the worst stick figure in the world. So we know it can't be gravitational force that are keeping all those particles together. Now, there's only one place in the universe where the strong nuclear and weak nuclear forces exist, and we're going to talk about these in Chapter 4 and 28. I underlined where they are. They're in the nucleus. So it is electromagnetic force that keeps all of these particles, these molecules, these atoms together. And magnetic force is governed by what's called Coulomb's law, named after the scientists who developed this. And Coulomb's law says that electromagnetic force, F, remember we've got a little vector here for direction, force has direction, is equal to K times Q1 times Q2 all over D squared. All right, so what does that mean? And you already know a lot about Coulomb's law. All right, Q1 and Q2 represent the electric charges. And we know that if these two things happen to be both positive, then we have repulsive force. And if they're both negative, then these forces repel. And the quantity that we come up with the force represents that repulsion, the particles pushing apart from each other. However, if one of them is positive and one of them is negative, then we have attractive force. So you already know about Coulomb's law. You know positive and negative is attract, and then like charges repel. And d squared represents the distance between those charges. Now do understand there's a lot of versions of Coulomb's law. This is the first derivative of it for all of you calculus people who love that sort of thing. But this algebraic interpretation is what we're going to use. And K is a proportionality constant, which means it's the number, the constant that's in the equation to make it work for that system. So all of this is governed by Coulomb's law. Positives attract negatives. Okay, so what does that have to do with compounds, elements, and mixtures? I'm glad you asked, because I'm going to tell you. The difference between the two is that with pure substances, that Coulombic attraction is very strong. That keeps those particles together. So we say strong attraction. And with a mixture, it's weaker. I'm not going to say it's a weak attraction. I'm going to write weak attraction. But the truth of the matter is, it's a weaker attraction. In other words, we react hydrogen with oxygen, and we get a compound H2O, water. It has totally different properties from the hydrogen and oxygen. The hydrogen and oxygen were colorless gases, and the water at room temperature and standard pressure is normally a colorless liquid. Okay. With a mixture, if you paint a car red, the paint sticks to the car via Coulombic attraction. The paint has some negative electrons in the paint, right? The metal body of the car has some positive protons in the paint. And the positives and negatives attract each other. but the paint just sticks to the surface of the car. You haven't created a new material. You haven't created rhodium chloride or rhodium monochloride. All you've done is stuck the paint onto the car. And that's easy to remove. It's like stepping in gum. If you get gum on the bottom of your shoe, you haven't created gummium shoeide. You can easily scrape the gum off. It's pretty gross. Or dissolve it with oil if you decide to do that with like cooking oil, that sort of thing. All right, so what type of materials are pure substances? And again, you are asking all the right questions. There are two types. There's elements and there are compounds. And mixtures, we're going to deal with colloids, suspensions, and homogeneous solutions when we do chapter 3. So we're not going to worry about it for now. We're going to focus on pure substances. All right, elements. You think of elements as atoms, but the truth of the matter is elements and compounds both have atoms. The difference is that when you're dealing with an element, every atom in that material is the same. So you have one type. And in a compound, the only difference is you have more than one type of atom. So example of a compound. Now we said H2O, water, CO2, carbon dioxide, those sort of things, right? More than one different type of atom. With an element, there are actually 3 different types of elements. And we expect you to know, wow, I am illiterate, sorry. Monoatomic. There's monoatomic, there's diatomic, and there's polyatomic atoms, or elements rather. And in a monoatomic, mono means one. So these particular elements are able to exist as individual units. With diatomic, they exist as groups of 2. There's only 7 diatomic elements. There's hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. There are 2 polyatomics, which means more than 2 atoms. They exist in groups of more than 2 atoms together, and one of them is phosphorus. It is what's called tetravalent, so it exists as groups of 4, and sulfur, which is octavalent, which exists as groups of 8. And the ones that it can exist as individual units are all the other elements on the periodic table. So we expect you to know which ones are monatomic, diatomic, polyatomic, and I know that requires a little bit of memorization, which is old-fashioned, but this will help you when we get to more difficult materials. I don't like students to memorize things. I like them to learn things so they can derive it. However, sometimes memorizing something is going to make it so that you can get to your goal faster, and these are timed tests, especially at the AP level. Everything is a time test, and sitting there and trying to derive which ones are which isn't going to help you. So you're going to memorize it, and that's where your blank periodic table comes in, because I'm going to show you an easy way to remember the diatomic elements. All right. First of all, phosphorus and sulfur. Go ahead and take your blank periodic table, and let's write phosphorus and sulfur in. And so we'll zoom in on this, and I'm just going to write P4 to remind me that that's tetravalent. And sulfur, I'm going to write S8 to remind me that that is octavalent. Now, to remember the diatomics, I'll do them in red. And this was shown to me by a student. I didn't make this up. If you put the diatomic elements in their right place, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and you connect them, it forms the number 7. And there are 7 elements. And then you're saying, well, where is the 7th one, hydrogen? Well, on this periodic table, hydrogen is located here. On some periodic tables, hydrogen is located here. I'm going to write H2 in its elemental form, not its atomic form. But on some periodic tables, hydrogen is not connected to anything else on the table because it doesn't behave like anything else on the table. So, you just have to remember hydrogen. And then a teacher, Mr. Ferraro, has a phrase, broccoli has no friends. So Br for broccoli, and nitrogen O, broccoli has no friends. H is the has part. I guess the Cl is part of the broccoli. I don't do it that way. You can figure it out on your own. Broccoli has no friends. I prefer the number 7 thing in the upper right-hand corner of the table to remember the diatomics. And that's it. Let me see what else we got, because we're getting long here on this video. Did I cover everything I wanted to? Elements versus compounds on it. Yeah, we're good. All right, so I will catch you young people on the next video. As always, thank you very much.